You're listening to DTFHN for June 16th, 2026. I'm your open source exhumed host, Jack Hacksman. We are your daily tech feed for Hacker News, a website where people who fix other people's bugs argue about whether that counts as a hobby. Today's a love letter to builders who ship because the craft demands it. Let's get into it. 65,536 individual write byte to memory instructions. Each one 4 bytes long, a quarter megabyte of machine code dedicated to doing what a 3-line loop could handle. Some compiler looked at a simple memory initialization routine and decided the optimal strategy was to unroll it completely, every single byte. This is a story from the early days of Windows running on non-x86 hardware, when Microsoft had teams building processor emulators. Binary translators that would take x86-32 code and JIT compile it into native instructions for whatever chip the machine actually ran. Think of x86 as a bytecode and the emulator as a just-in-time compiler. Clever engineering that let legacy software run on new architectures without anyone recompiling anything. The emulator team encountered a program that needed to allocate 64 kilobytes on the stack and zero it out. Standard practice. You do a stack probe, subtract from the stack pointer, run a tight loop. Done. But whatever compiler built this binary had other ideas. It unrolled the entire initialization into individual store instructions, inflating a trivial operation into a bloated monument to premature optimization. And here's the part that matters. The emulator team didn't just shrug and translate it faithfully. They were so offended by the code that they wrote a special case into the translator to detect this specific pattern and replace it with the loop it should have been in the first place. They fixed someone else's code during emulation. The program ran faster on the emulator than it would have on native x86 hardware, because the emulator team cared more about the code quality than the original compiler did. This is builder culture at its finest. Engineers who could have moved on, who had no obligation to optimize someone else's mess, chose to make it right because the craft demanded it. The comments surface other examples. Microsoft famously patched Windows 85 to work around a read-after-free bug in SimCity rather than waiting for Maxis to fix their game. The Proton compatibility layer on Linux does similar work today, where the open-source community patches around broken PC ports that the original publishers won't fix. Elden Ring reportedly runs better through Proton than it does natively on Windows, because people who care about the experience stepped in where the vendor wouldn't. There's a pattern here worth naming. The people closest to the metal, closest to the users, doing the unglamorous work of making things actually function. They're the ones who fix it, not because they ship the bug, because they can. And nobody embodies that fix-it, because you can spear it quite like Fabrice Bellard, who John Carmack just called the most productive programmer in history. Someone in the comments said seeing Fabrice Bellard's photo felt like unmasking Satoshi Nakamoto. And that comparison tells you everything about how broken our understanding of influence actually is. In mycology, there's a concept called the Wood Wide Web. Beneath every forest floor, fungal networks connect the roots of trees across enormous distances, shuttling nutrients, passing chemical warnings, keeping the whole system alive. The trees get the credit. They're visible. They're majestic. Nobody photographs the mycelium, but without it, the forest collapses. Fabrice Bellard is the mycelium of modern computing. FFNPEG. Every video you have ever streamed online was decoded by his code. YouTube, Netflix, TikTok, Discord, VLC, OBS, your browser's video player. All of it traces back to a codec library one person in Paris started writing and then just kept making better. QEMU, the virtualization layer underneath half the cloud infrastructure on Earth. The thing that lets you run a Windows VM on Linux, an ARM emulator on x86, entire data centers of simulated hardware. He wrote that too. Tiny C compiler, a C compiler that compiles itself in under a second. He built it partly to prove it could be done. He also held the record for computing the most digits of pi. He also built a 4G LTE base station by himself on a PC. One commenter shared that they emailed Bellard in 2013 and got back a quick, humble, valuable response. Another described building an entire platform as a service on top of QEMU at their first job out of university, just for fun, because the tool was that good and that available. This is what happens when foundational software ships without a licensing team, without a developer relations strategy, without a conference keynote. It just works, and people build on it, and the building never stops. John Carmack calling attention to Bellard is one living legend recognizing another, but there is a crucial difference in how the world treats them. Carmack built Doom and became famous. Bellard built the plumbing under every screen on Earth, and most engineers couldn't pick him out of a lineup. The bemusing part isn't the obscurity. Plenty of brilliant people are obscure. The bemusing part is that Bellard's work is open, every line available to anyone. The entire internet is built on code. You can read, modify, and redistribute, written by someone who apparently just wanted to solve interesting problems and then move on to the next one. That's not a tragedy of under-recognition. That's the model working exactly as intended. Now, not everyone contributing code has pure intentions. Story 3 opens with a Lincoln message that turned out to be anything but a job offer. Line 225. That's where it lives. Not line 1, not the entry point, not anywhere you'd look first. Line 225 of a file called index.js inside a folder called test, surrounded by commented out test cases that nobody would ever bother to read carefully because commented out tests are the universal signal for someone was lazy here, move along. And that's the craft. That's what I want to talk about. A developer named Roman got a LinkedIn message from a recruiter at a crypto startup. Normal enough. They exchanged messages over a few days. She described a broken proof of concept, asked him to review a GitHub repo, and specifically told him to check out the deprecated node modules issue, which is another way of saying, please run npm install. Here's the devil's advocate angle. You could argue this is sloppy, a URL assembled from string fragments. Protocol, domain, separator, path. Like a kid hiding a note in a cereal box. Surely any decent engineer would catch this. But play that forward. Would you? You've got a repo that looks like a React frontend with a Node backend. The package.json wires a prepare script to run on install. npm runs prepare automatically after npm install. That's not a bug. That's npm working exactly as documented. The attacker didn't exploit a vulnerability in the toolchain. They exploited the toolchain working correctly. The prepare hook fetches a URL, downloads whatever the server sends back, and executes it. Your machine is now running arbitrary code from a stranger's server, and you invited it in by doing the thing every developer does 40 times a week without thinking. What Roman did instead deserves the admiration. He spun up a throwaway VPS, cloned the repo there, and pointed an AI agent at it in read-only mode. No write access, no execution, just file reading tools. The agent flagged line 225 in seconds. Faster than a human would have, because humans self-select past commented out code. We're trained to ignore it. The agent wasn't. The commits were authored under a real developer's name. The recruiter's profile belonged to a real arts journalist. Both identities stolen. When Roman told the recruiter he couldn't get the project to install, the arts journalist suddenly became an expert on node version compatibility. That's the tell that should make every hiring manager on LinkedIn uncomfortable. Roman reported the repo to GitHub and the recruiter to LinkedIn. As of his writing, nothing had changed. The code was still up. The profile was still active. One comment on the thread put it plainly. This is uncomfortably close to a normal interview task now. Someone sends you a repo, says the install is broken, asks you to take a look. The distance between a legitimate technical screen and a supply chain attack is exactly 1 npm install. The tooling to verify before you execute exists. Use it. A read-only agent and a disposable VM turned a potential compromise into a blog post. That's the engineering response. Not less tooling, but better hygiene with the tools you already have. So what happens when you point all that computational power at something purely beautiful? Let's talk generative art. I have enough from the article text provided. Let me write the script segment. There's a moment in every engineer's life where you stare at a system doing something you didn't explicitly tell it to do, and you realize the beauty was always in the constraints. I hit that wall building procedural terrain generators years ago. You tweak 3 parameters, and suddenly the output looks like satellite photography of coastlines. The machine isn't creative. The math is creative. You're just finally listening. Murtaza Hussain, a PhD student looking for a break from academic grind, decided to test this idea systematically. He picked one algorithm, Perlin noise flow fields, and challenged himself to produce as many distinct visual designs as possible without changing the core process. 25 variations, same engine, same math, same canvas. The technique itself is elegant in its simplicity. Imagine a 2-dimensional force field where every point on a canvas has a direction. Drop particles onto it and let them drift. With pure randomness, you get visual static. But Ken Perlin figured this out back in 1993, while working on the original Trump. Replace random values with smoothly interpolated gradients, and organic structure emerges from nothing. Rivers of motion, topographic intuition, the kind of patterns your brain reads as natural, even though no natural process produced them. What Hussain discovered mirrors something fundamental about creative engineering. By iteration 3, white particles on black, then hand-picked purple palettes layered dark to light. He thought he was already out of ideas. 3 variations, and the well felt dry. But he kept going. He dropped opacity to 1% and watched gray materialize from thousands of nearly invisible strokes. He varied particle counts, stroke weights, color mapping strategies. 25 distinct outputs from one algorithm. The entire codebase is on GitHub. Processing sketches, animated GIFs showing the generation process, everything. You can fork it and start iterating in minutes. Another artist, Damoun Rashidi, independently explored the same technique and published their own variations with live sketches. This is how open creative tooling compounds. One person's weekend experiment becomes another person's starting point. The real lesson here isn't about Perlin noise. It's about what happens when you hold the algorithm fixed and let yourself play within constraints. Creativity isn't the absence of limits. It's the pressure they create. Every parameter you refuse to change forces you to discover something in the parameters you kept. That's craft. And the fact that the blueprints, the code, the process animations are all sitting in a public repo means anyone with curiosity in a weekend can pick up exactly where Hussein left off and push further. Moving on. What if the internet got the address system backwards from the start? Not maliciously, just pragmatically. In the 70s, when you were bolting together a few dozen research machines, numbering them by location made perfect sense. Your address was where you were. And then we spent the next 50 years building increasingly baroque tanged workarounds for the fact that devices move, networks change, firewalls exist. And that is a thing. We papered over a fundamental architectural choice with DNS, with VPNs, with stun servers, with tailscale, with an entire industry of please let me talk to the computer I already know I want to talk to. Iroh just hit version 1.1 and in it asks the question nobody in networking wants to sit with. What if your address was your key? Not your IP, not a domain name that resolves to an IP that might change. A cryptographic key that you generate, you control, and that stays the same whether you're on hotel Wi-Fi in Osaka or tethered to your phone on a train in Belgium. The key is the identity. The key is the address. The key secures the connection. One abstraction doing 3 jobs that currently require entirely separate stacks. The engineering underneath is genuinely clever. They built quick multipath so a single connection can hot swap between routes as conditions change. They implemented quick NAT traversal with encrypted connection details. It compiles to WASM and runs in the browser. And they've opened up custom transports so you can plug in Bluetooth Low Energy, LoRa, Wi-Fi Aware, even Tor. And it all sits under the same dial-by-key interface. 200 million endpoints created through their public relays in the last 30 days alone. One commenter nailed the mental model. Tailscale at the application layer instead of the network layer. But that undersells it. Tailscale is a product you adopt. Iroh is a library you embed. Your Swift iOS app, your Kotlin Android app, your Python backend, they all just get this capability. And 95% of data goes direct, device to device, fewer hops through the cloud, lower egress bills, less load on the infrastructure we all share. 4 years of building in the open, IETF drafts where possible, Rust crate plus official bindings in Python, Node, Swift, Kotlin. Wire protocol stability guaranteed across the 1.0 lot. The internet was built on the assumption that location is identity. Iroh is built on the assumption that identity is identity. It's the kind of correction that seems obvious in retrospect, which is exactly how you know it's right. This one made me grin. 4 megabytes. That's the constraint. An ESP32C3 microcontroller inside a commodity smart light bulb. 4 megabytes of flash total. And that has to fit the firmware, a web server, and the books themselves. The entire project lives inside that boundary. Richard Osgood's banned book library is a light bulb that broadcasts an open Wi-Fi access point and serves banned books to anyone who connects. Screw it into any standard socket, flip the switch, and it becomes a node in an invisible library network. The device draws power from the fixture. It looks like a light bulb because it is a light bulb. it still produces light. The extra functionality is, architecturally speaking, a parasite riding on the power delivery system that already exists in every building on Earth. The tuba path is worth tracing. These bulbs ship with Tasmota, an open-source firmware designed to liberate smart home devices from cloud dependencies. The manufacturer even documents the GPIO pin assignment. Red on 6, green on 7, blue on 5, cool white on 3, warm white on 4. That level of transparency only exists because the firmware is open. Tasmota's over-the-air update mechanism means you can reflash the bulb without cracking it open, without soldering, without a serial programmer. You push new firmware over Wi-Fi, and the device becomes something its manufacturer never intended. This is what open architecture makes possible. The bulb manufacturer published the specs because Tasmota's ecosystem rewards transparency. Osgood used that transparency to build something the manufacturer never imagined. The open-source supply chain didn't just enable the project. It made it inevitable. Someone was always going to do this. The 4 megabyte constraint is real, though. Firmware plus web server plus content has to fit. A novel in plain text runs maybe half a megabyte. You're looking at maybe 5 or 6 books per bulb depending on compression. That's a limitation, but a limitation distributed across 100 light bulbs in 100 locations is a library. The comments mention Pyrobox, a similar concept from 2012 using flashed Wi-Fi access points. The lineage matters. These ideas keep recurring because the fundamental engineering is sound. Commodity hardware, open firmware, local first distribution. Every generation of cheap wireless hardware makes it easier and cheaper. A light bulb, serving books, drawing power from the building that houses it. The elegance is in the banality. Nobody audits their light bulb. So we're putting libraries in light bulbs now. What else can we run locally? Turns out, maybe your entire coding assistant. In Don Buenas Core was a payable azabe into Cornerstone Ardquig or my Tanger Selbo. In Doom, Sumter's sake Beanums, Ian. Academics agreed. The theory was settled, and Linus shipped anyway, because the code worked and it was free. And that turned out to matter more than architectural elegance. This thread on Hacker News is that same argument happening again in a different room. The question is simple. Can you replace Claude or GPT with a local model for real coding work? And the answers split exactly where you'd expect. One camp says the opportunity cost is too high, that frontier models are advancing so fast, you'd be leaving capability on the table. The other camp is just shipping. Qwen 3.6 on a single RTX 3% and 90. Gemma 3 on a Mac Studio with 128 gigs of RAM. People wiring up local inference with open code. Custom skills, containerized harnesses running fully offline. One person reports 90% of their coding happens on a 27 billion parameter model running on consumer hardware. Strip this down to first principles. What does a coding assistant actually need to do? It needs to understand context, generate plausible code, and iterate on feedback. The frontier models do this better. Nobody disputes that. But better by how much, and at what cost? The local setups people describe here perform like cloud models from 8 to 12 months ago. For most daily coding, that's sufficient. More than sufficient. The cost calculation isn't just dollars, though. It's sovereignty. Every query to a cloud model is a dependency on someone else's infrastructure, someone else's pricing, someone else's terms of service, someone else's decision about what your data trains next. A model running on your own hardware is yours. It runs when the API is down. It runs when the company pivots. It runs when the pricing changes. The commenter running behind PI harness pointed at Unsloth Studio, fully offline, containerized, and sandboxed. That person isn't making a compromise, they're making an architectural decision. The same one Linus made, the code works, and it's free, and 35 years later, that still matters more than theoretical optimality. The models will keep improving, the hardware will keep getting cheaper, the gap between local and cloud will keep narrowing, and every month it narrows, another engineer realizes they can own their tools instead of renting them. Moving on. Defend the driver developer for a moment. They read the documentation. They saw the rules. Don't block in your callback. Don't make slow API calls. Use system worker threads to offload expensive work. They did exactly what the docs said. Queued their work to a worker thread, textbook compliance. The fact that they then sat there waiting for the result. Well, there's no rule that says don't wait for work items. They found a gap in the spec and threaded the needle. Clever even, except the system hangs. Every time, this is Raymond Chen documenting what Microsoft's enterprise support team keeps finding in the wild. Driver callbacks that technically follow every listed prohibition while violating the single principle underneath all of them. The callback must return fast. That's it. That's the entire law. Everything else is just examples of ways you might break it. The developer read, "Don't synchronize with other threads," and thought, "I'm not synchronizing with a thread. I'm waiting on an event." The event happens to be set by a thread, but that's the event's problem. Chen's colleague calls this the "it wasn't me, it was my brother" defense. You were told not to turn on the television, so you told your brother to do it. Technically clean, functionally identical. Run this forward. Imagine every rule in every system had to enumerate every possible evasion. So no callback documentation would be infinite. Don't wait on events. Don't wait on futures. Don't wait on promises. Don't pull in a tight loop. Don't yield and check. Don't set a timer for 1 millisecond. You'd be writing case law instead of engineering guidance. This is why the best documentation states intent before listing prohibitions. Microsoft actually updated the docs in 2020 to close this specific loophole, which is both responsible and quietly hilarious. An admission that someone somewhere shipped a driver that hung production systems because the spec had a gap between "don't block" and "don't wait for the thing you offloaded." The comments nail it. One reader connects this to Chesterton's fence. Understand why the rule exists before you decide you found a clever way around it. Another points out that Chen writing a blog post about a doc's improvement, instead of just making the improvement, says something about Microsoft's own internal friction. Conway's flaw, they called it. The documentation is public, the blog is public, the lesson is free, and the lesson is simple. If you understand the principle, you don't need the exhaustive list. If you only follow the list, you'll find the one thing it forgot to mention. So what happens when someone takes that principle-first mindset and applies it to wind physics in a browser? Something delightful. 380,000 kilometers sailed. That's roughly the distance from Earth to the Moon, sailed by players in a browser game about pixel pirates and wind physics, built by what appears to be a solo developer inviting playtest feedback from 245 active captains. Let's pull this thread on the physics. The comments split into two camps, and both are revealing. One group wants more. Real sailing mechanics, tacking penalties, the actual cost of beating up wind. They want the simulation. The other group is already hooked, playing for 30 minutes on a phone browser without a single crash. They want the gain. And the developer threaded that needle in a way that deserves admiration. Real wind physics in a browser-based pixel art game is a genuine engineering challenge. You're simulating fluid dynamics, particle systems, directional force vectors, all running in whatever JavaScript engine Firefox on Android decides to give you that day. The fact that it works flawlessly on a 6.1-inch phone screen is not an accident. That's careful, disciplined engineering underneath the charming pixel art. The game is free, runs in your browser. The developer is in the comments asking for feedback, not pitching a subscription tier. This is builder culture at its purest. Someone who wanted a sailing game with real wind, so they built a sailing game with real wind, then put it where anyone could play it. One commenter nailed the aspiration: slower pacing, real-world maps, historical naval battles. That's not criticism. That's someone seeing the foundation and imagining the cathedral. The tools exist. The engine works. 380,000 kilometers of proof are already on the water. Now shift gears entirely, from building new worlds on open water to rescuing one that almost disappeared from the web. A comment on Hacker News tells the whole story in 3 sentences. Trinket.io is shutting down in August. They open-sourced their code in March. Nobody was hosting it because the server costs are brutal. Then Strive Math picked it up. For anyone who hasn't used it, Trinket is a browser-based coding environment. Python, HTML, music, visual art. Designed for education. Teachers embed it in lesson plans. Students run code without installing anything. It's one of those tools that quietly underpins thousands of classrooms, and you never hear about it until it's about to disappear. The original company couldn't sustain the business model. That part isn't surprising. Education technology has a brutal economics problem where the people who need the tools most can afford them least. What matters is what happened next. The team didn't just shut the doors, they opened the code. They gave the community a chance. And someone took it. Strive Math is now running the full platform at trinket.strivemath.org. Every feature unlocked. No paid tiers, no trials. Free forever. They used their Y Combinator network to find the resources to absorb the hosting costs that scared everyone else off. This is bootstrapism working exactly as designed. The tool exists. The code is open. When the original steward can't carry it anymore, someone else picks it up and keeps going. The ladder stays down. Every teacher who built a curriculum around Trinket, every student halfway through a Python lesson, they don't lose anything. Pull this thread forward. Every piece of educational infrastructure that locks its code away is one bad quarter from vanishing and taking the classroom with it. Everyone that opens its source is a seed that can be replanted. Trinket just got replanted. This has been your daily tech feed for Hacker News for June 16th, 2026. This podcast is entirely AI-generated. Decrypts by Claude Sonnet 4.7. Voice by Quen3TTS. Not affiliated with Hacker News or Y Combinator. Now go build something worth passing on. We'll see you back here tomorrow.